So let's see, trial 1 when n equals 1, okay, in the formula. So use the largest one, intensity, I sub I equals, 5. Well, it says I sub 3 because it's the third number in the data, okay? So we have Q equals, I sub 3 minus 5 times delta T. So we know Q is 3.6, delta T is 30 minutes. So that's 0.5, hours, okay? So 0.5. And then we know, I sub 3 is 5. And then if you solve this, then eventually you get phi equals minus 2.2 centimeters per hour. So this is invalid. Infiltration cannot be negative. So n equals 1 does not work. Okay. So trial number 2, n equals 2. So again, we use the two largest intensities. So 5, 3.6. And then we get phi equals 0.7 centimeters per hour. So phi 0.7 equals to 0.67 is less than 5 and 3.6. So it works, but phi must be greater than rainfall intensities not producing runoff, like 2.8 and 2.2, etc. And 0.7 is too small. This would allow too many intervals to produce runoff, so invalid. So what this means is that we have, so this is the data, right? But right now our phi is equal to 0.7. So you see how all these numbers are greater than 0.7. So if we have 0.7 as phi, then there's zero infiltration. Okay. Now this is not really possible, so this is invalid. Okay. So the next one, trial number 3, n equals 3. So again, we use the largest values. We get phi equals 1.4. Okay, so phi is, when it's 1.4, it's less than these three, so it's okay. But phi must be greater than 2.2 only if 2.2 is excluded. But since phi is less than 2.2, rainfall at 2.2 centimeters per hour also produces runoff. This trial underestimates n, so invalid. So n equals 3, and we have, again, our value is 1.4. N equals 3. Yes, so when n equals 3, we're saying the number of rainfall intervals contributing to direct runoff should be 3, right? But instead of having 3 intervals contributing to the runoff, we have 1, 2, 3, and 4. So we should only have 3 intervals contributing to the runoff, but instead we have 4 because these 4 are all greater than 1.4. Okay, so this is invalid. Alright, so that's the reason why this is also invalid. So if we look at the summary table, n equals 1, invalid, 2, invalid, 3, invalid, and when it's 4, we get the phi result of 1.6, and then the number of intervals that contribute to the direct runoff is also 4. So n equals 4. This matches, right? So this is valid. Okay, so using the trial and error method, we got, n equals 4 is valid. So using n equals 4, we get phi equals 1.6 centimeters per hour. And then for W index method, we're using the, W equals F over T sub D. And then F can be rewritten as P minus Q, minus D. But if you remember, from the problem, it said the initial abstraction is 0. Okay, so D is 0. All right, and then so we have 8.1 centimeters as the total precipitation, right? So 8.1 minus the 3.6, which was given, divided by 3, which was also given, and then we get 1.5 centimeters per hour from that. Okay, and the solution is shown in figure 6.19. So this is figure 6.19, 6.19. Infiltration rate by phi index and W index. So you see that the dotted line is phi index, so this line right here. And then the full line is W index, so this. So you see that how like the W index is lower than phi index, and we can say that everything, we're using W index, everything below this line is lost to infiltration, and for phi index we can say everything below this red line is lost to infiltration. But everything that's above the line, that's direct runoff. Okay, so let's now look at the theory of unihydrograph, definition of unihydrograph. So a unihydrograph of a watershed is defined as a direct runoff hydrograph resulting from a unit depth of effective rainfall of uniform intensity distributed evenly over the entire watershed area for a specific duration. In other words, as shown in figure 10.1, when 1 centimeter of effective rainfall occurs uniformly over the entire watershed, the resulting direct runoff hydrograph at the watershed outlet is called the unit hydrograph. So, if we have a watershed like this, and then there's rain coming down, we're saying this rain that's falling down is has a unit depth of effective rainfall. So part of the rainfall will be effective rainfall, okay, and it will come with a unit depth. So it's only going to have like 1 centimeter of depth of rainfall that's going to be effective rainfall, okay? And it's going to uniformly fall over this entire watershed. So it's going to reach the surface of the watershed like evenly, okay? So that's what it means. And then the resulting runoff we get at the outlet of the drainage area, so like at the end, like right here, so the direct runoff hydrograph at the watershed outlet, so outlet is here, so the direct runoff hydrograph we're going to get at the end right here is called the unit hydrograph. Okay, so if we look at figure 10.1 concept of unit hydrograph, we have the rainfall intensity, and then we have the unit effective rainfall, so that's this block, okay, 1 centimeters, and then we have time, okay, so we have the time on the x-axis and then the rainfall intensity on the y-axis for the unit effective rainfall, and then we get the discharge at the end of the watershed, the direct runoff, and then so it's discharge on the y-axis. And then we have time, at the x-axis, T sub B, and then we call this unit hydrograph. Okay, so this, we call this unit hydrograph. And then the area of the unit hydrograph is 1 centimeters times the watershed area, because there's 1 centimeters of effective rainfall. And then this is happening at the outlet of the drainage area. So the area of the unit hydrograph is 1 centimeters times the area of the watershed. Okay. So 10.1.2 assumptions of the unit hydrograph. The theory of the unit hydrograph is based on certain assumptions regarding its definition and characteristics. The main assumptions of the unit hydrograph are the principle of equal base time, the principle of proportionality, and the principle of superposition. Okay, so the first one, principle of equal base time, as shown in figure 10.2, when there are effective rainfalls of different rainfall intensities but with the same duration, So the intensities I's are different. Okay, so I's are different, but T's are the same. Okay, so I is not the same, but T are the same. So in this case, the resulting direct runoff hydrographs will have the same base time T sub B, and their time to peak will also be the same. So if you remember here, it's saying if there are two different rainfall intensities, so rainfall intensity number 1 and the rainfall intensity number 2, but they have same T, okay? So same T. So in this case, the resulting, the direct runoff hydrograph will have same TB, okay? Even if they look, different, the TB will be the same. Okay, let me, so even if it looks different, it's going to have same T sub B, and the time to reach its peak will also be the same. Okay? This assumption is called the principle of equal base time. So like what I just explained, principle equal base time and principle of proportionality. Okay, so this is actually showing both the equal base time and also the principle of proportionality. We'll come back to this figure after talking about it, but so we have the same base time T sub B, and then we have unit effective rainfall, and then time, and then we also have time. So time on the x-axis here, x-axis here, and then we have the rainfall intensity on the y here, and then the direct runoff on the y here as well. So we have I, and then the above it is called Ni. So it just means, this is I, and then it's I multiplied by n value. Okay, so there's a ratio of how much I is being increased, and same thing happens down here. So Q, and then there's a n value that's being multiplied to Q, right? And then just like how it's happening intensity, how it multiplied by n, increased by n, this also gets increased by n, and that's what's happening, and it's happening proportionally. Okay, so that's why it's called proportionality, principle of proportionality. So as shown in figure 10.2, let an effective rainfall of intensity I produce a unit hydrograph with peak discharge Q, and let an effective rainfall that is n times larger Ni produce a runoff hydrograph with peak discharge NQ. So just like I said, I increased by n, so Q increased by n. Okay, since the ratio between the rainfall intensities is proportional to the ratio of peak discharges, the relationship between effective rainfall and direct runoff is linear. This assumption is called the principle of proportionality. So the last one is principle of superposition. So as shown in figure 10.13, so that's this figure down here. Suppose there are two effective rainfalls P1 and P2. So P1 and P2. When these two effective rainfalls of different magnitudes occur over a watershed, the resulting direct runoff hydrograph can be obtained by summing the individual direct runoff hydrographs corresponding to each rainfall as described in 1 and 2. So again, we have the effective rainfalls, right? And then rainfall intensity on the y-axis, and based on the rainfall, we get the discharge hydrographs, right? So it's saying, based on the first, effective rainfall, you can draw this hydrograph, number 1. And then based on this second one, you can draw the second hydrograph. And then when you combine, add these together, and make one big one like this. So basically this number 3 hydrograph accounts for both of these effective rainfalls. Okay, that's basically what's happening. Okay.